So, welcome to my talk. This third talk. Yeah. Not collapsing? Still hungry? Okay. So, my name is Angel Bertini. I'm doing reverse engineering and visual documentations. This is how you can contact me. And I'm the author of a website called Corkamy, where I share my findings and stuff. Even though now I share more of my stuff on my Twitter, and I don't update the website so often, but yeah. And so let's start with a small sentence. An encrypted file is not always encrypted. In the sense that if you take a file and you encrypt it, you operate an encryption on it, then how we see an encrypted file usually is that the output is random. Okay, what does that mean? Let's take an example. This is a random JPEG picture. And if you encrypt it with AES, you get this picture, which is a random PNG picture. And if you take the same file, same JPEG, but you decrypt it with triple des, because why not, you get this random PDF. So don't worry, I'll keep it simple, because I suck at crypto, and crypto is too hard anyway, especially for me. And this is my usual reaction, which is good for you, because I only explain it in very simple ways. So let's just play together with different tool set of games together. And this is crypto, the TrueCrypt format and the PNG format first, and TrueCrypt then. So let's start really, really slowly with AES, Advanced Encryption Standard. I don't care about how it's inside. AES is a block cipher. It takes a block of 16 bytes, a key of 16 bytes in the case of AES 128, which is what I will use from now on, but it doesn't really matter. And then after it returns as output a block, a different block of 16 bytes. So, for example, a block of text, a key, and you get something starting with BF11, whatever. If you change the key just a bit, the result is completely different, starting with 67.4F. Or if you change the initial input block, once again, completely different result. Okay, big deal. So any change in the key or input block gives a completely different output. We can't control the output because of that, because the differences when changing everything is completely are unpredictable. The opposite operation, because encrypting wouldn't make sense if you cannot revert the operation, yeah? So you had an operation of encryption, which was giving you this, and now you can recover the result from the same key and the encrypted block. So now the encryption block makes sense for decryption, and you get back the original content. Cool. And if you change the keys slightly, you get a completely different result, which means that with the encryption key, we can restore the original block, and without, okay, I'm not a cryptographer, we can't do anything. Just assume we cannot do anything. I'm not a cryptographer anyway. So, an important fact is that plain encrypted are just names. There is not one function that says, hey, that's English, let's encrypt it, and the other says, oh, that looks random, let's put it back to English. They are just inverse function, bijections, both of them, encryption and decryption, and just inverse functions. So, we were encrypting plain text to something that looks random, but actually we could just do the opposite, decrypt plain text, we get something random, something else, and again, by the inverse operation, we get back to the original block. So then we have actually, we can control the output of encryption if we cannot control the input. We can decrypt plain text and we recover the original block via encryption. So we can control encryption output. So to recap the part on crypto, really simple stuff. AES encrypts a block, and we don't control the output. The encrypted block can be restored with the right encryption key. Encryption and decryption are just inverse function. We can decrypt plain text, and we can recover the original block via encryption. But we cannot control both, one or the other. So now let's talk about something different. Cow. This is a cow. Well, this is how users and normal people, standard people see it. This is how an expert sees a cow. Still the same cow, but it just has some internal structure. And if you notice the standard, this is the German and French standard of the internal structure of a car are different. Anyway, well, I won't study the all internals of a car. Let's look with a simplified structure. Signature, header, data, and easy chunks. One important fact in real life, or what will come later, is that if our car swallows a micro SD, it's still a valid car, even if it contains foreign data and it's tolerated by the system. It contains 64 gigabytes of data, of foreign data, but it's still a valid car from the outside. So now that gives you an idea of what I'm leading to. Okay, now let's go back to non-cows, because I'm not a cow expert, obviously, or you don't yet, maybe, who knows. But actually, I have more cows. I applied for a different talk at the CCC, and I have much more. The alternate title is like explaining a binary with cows. So it's like full of cows, many more cows. Anyway, sorry for that. So let's look at, a bit more binary, the PNG file format, PNG file format. So made of signature and chunks, and here we have header, data, and end. So now, let's forget the cows, but still you have the idea of them. So the chunk is each, like the beef chunk, the format is made of variable size pieces. These chunks could be very critical, like if you remove the head of a cow, I'm still not sure it's a valid cow, but maybe there are some part of the cow that you could remove and it still survives or something. Or you still, without the tail, you would still consider it a cow. Yeah, maybe, I don't know. Let me know if it doesn't work. So basically, chunks are just a common high-level structure, independent of the content and its interpretation. The idea is that there is something standard to guarantee minimal compatibility between all the files, the tools manipulating this file format, and you could still store proprietary information, like the cow swallowing a micro SD. It's still a valid cow. So now let's take a real example that you may have seen somewhere before, and we'll take a tool that is called hachoir, which means meat grinder, which is a tool for computer butchers. So you see the comparison with cows still goes on. So now that's what hachoir looks like on the Google file. So you have a signature and a series of chunks, 3 chunks. And so the chunks at a high level have the same structure, but then 3 different chunks in their type. So first the signature, which is enforced at offset 0. The signature is made to say it's a ping, and also the signature was crafted so that you could detect standard error, transfer errors. So if it was transferred as text or if it was transferred as ASCII, then you could determine that from the signature. So here is our signature. And the chunks at high level, they have a common structure, so a size of the chunk on 4 bytes, then the type. If the first letter of the type is lowercase, then this type is ancillary. And if it's uppercase, then it's critical. So if this chunk is invalid or missing, then the file is considered corrupted. Then the data of the chunk, whatever it is, and the checksum of the chunk. And remember, we can add custom chunks. So in a Google example, we have 3 chunks. So let's look at the header chunk. So as usual, always the same structure, the size and the tag. And then an interpretation of the content of the chunk, which is here, the image information. Now, if you look at the IDAT chunk, if we go back and you get a poster, you have some more understanding in this. But basically, the IDAT means it's the pixels in zlib format. So basically, this could be stored decompressed, and now we have a slot of FFF0, which means black pixels with transparent. So that's what you see in the background. That's the background of the picture. I mean, in the corners. And then you have an end chunk. What is the purpose of an end chunk? Is that at least it tells the parser, okay, the end is reached, the end is near. No, well, the end is reached. The end. And then it means don't parse any further. So the use of that is that on the Google side, it's like this. On the Google picture, it's like this. But if you add a lot of data, the file is still valid because at some point you say, this is the end of my file. So that's why there is an end chunk. Of course, if the end chunk was missing, maybe the file was still parsed, but that's another story. At least this makes it makes validate the file, and then after whatever comes after is just ignored by the parser. It doesn't waste any more time processing the file. So a recap on the PNG file format, on the PNG file format, signature offset 0, then a sequence of chunk, in our case, header, data, and end. And the end is always strictly the same. It's basically it's empty, but the type is fixed, I-end. So now you can claim that you know how Google works by pointing this picture, and impress your friends. Now let's look back at our crypto tricks. If you take a valid chunk, start of the file, of a PNG file, and we take a key, then you will get something random, which means this is not a valid ping. The encryption breaks the signature that you would expect to have a valid file. So if you use file, here it says ping image data, and then it says random. So without the signature, the encrypted file is invalid. I mean, the first block being encrypted leads to an invalid file. If we encrypted a ping, we don't get a ping. It's because a priori, the signature is broken and the structure too. So how could we encrypt Google into DuckDuckGo? How can we control input and output, which is the challenge here? So AES is a block cipher. It works only with blocks. It doesn't care what a file is. How can we use it on a file? So if we would take each block and encrypt them independently, then identical blocks would lead to identical encrypted result, which leads to the famous ECB mode, which is a mode only for students, I'd say. I mean, totally useless in the matter of security, but it's the result you see. It doesn't look really encrypted, right? So that's not, because you would want a single change at the beginning to propagate on the whole file. So one of the modes to encrypt a file is that you actually take each block of the file and you propagate some consequences of the previous encryptions. So basically you have an external parameter, the initialization vector, that is XORed with the initial plaintext block. And then the result of encryption is also used to XOR on the same block, and it's chained like this. So basically a change here would make some change here, which would make some change in what's the result here. You can do the reverse operation, but at least this will provide better encryption. So cipher block chaining, it's considered secure, and we'll use it from now on. So when I say AES, it's AES CBC. And so this initialization vector. In practice, it should be unpredictable. And it's an extra parameter, but you can choose it to any value. It's arbitrary. So now let's look again. We have for a file, now we use a key and an initialization vector, and it works on X blocks, and it gives you X blocks. That's how it will work on a file. So now if we look back at the file, we see that the first ciphertext is the encryption of the XOR of IV and the first plaintext block. And if we apply decryption on that, it cancels each other, and we have now decryptions of the first cipher is equal to this, and if we XOR on both sides, then it cancels each other, and then we have a relation between the IV and the actual first plaintext block and first cipher block. So now we have this value. So basically, if we know that we want the file to encrypt as in the first ciphertext block, and we know what the file was originally starting as, we can craft an IV so that it will work. So we decrypt ciphertext and we apply XOR with this with P1. So basically, we have this, and we want this to encrypt as this. So we choose a key, random key, and we apply this formula. Here, this is a standard EBC mode decryption, and we get this. And indeed, this encrypts this first block as this first block. We don't control what will come next in the next block, but at least we got now a valid signature because we got the first cipher block. We get a valid signature, and because the block is 16 bytes and the signature is 8, we have 8 extra bytes. We control nothing else so far, but no valid structure, but it's better than nothing. So how can we control the structure via encryption? If we encrypt picture of Google, and we get this encrypted result, whatever. Because encryption is just depending on what was coming before. If you add something to it, it doesn't change and you perform a decryption, it doesn't change the fact that these blocks were not chained and the operation is still working from the same for what was working before. Because you only modify, you only alter what will be encrypted in the following blocks of the file and not in the previous blocks that were already encrypted or decrypted. So basically you open DuckDuckGo, you decrypt the whole file, you get your Google stuff, you get your Google, of course that's a raw image, not PNG. And you get some random data, and if you encrypted that, then you get back, you get your random stuff, but you get back the images that you wanted as a result of decryption. Remember, this is just image data. This is not here, well, you can maybe see it coming, but this is just image data, not file-wise, because of the first block. So if we pre-decrypt data, we decrypt the target chunks and we append them, then when it will be we append them to at the start of the next block, of course, so that there's no corruption on the last block of Google. And then it will still be valid because of the IN chunk at the end of Google. The rest of the file doesn't matter. So the Google logo is still okay. And it can piggyback some extra data that when encrypted, will become the DuckDuckGo data. Now we control a bit of the input and a bit of the output. The source file is still valid because it was the original Google file with some appended data that happens to be the pre-decrypted data of the DuckDuckGo logo. So now we just have a problem. How do we control this data, the encryption of the Google, so that this file becomes valid and not just image data? Well, we don't. And like the micro SD in a cow stuff, we just ask the file format to ignore it. I don't know if you see the parallel yet. So if you remember, we can add a micro SD in a cow, we can add an extra chunk in a PNG file with your own data, whatever it is. The position doesn't matter. And you can even create whatever name you have. And as long as the first character of the name is lowercase, then this will be ignored by parsers which are unlikely to support it. So basically, it's a very easy way to add foreign data in a file, in a PNG file in this example. The one thing important is that, in theory, the image header chunk should be the first. In practice, no tools care about this. So basically, except Ashwar, sadly, the tool I'm using to show is the only tool that I could find that actually cares about this. So basically, you could, even before the header itself, you could add your own custom chunk with any data you want. And because after this valid chunk, even if foreign, you could have your header and the rest of the file, the file will still be considered valid. So now we can add custom chunks, and as a recap, the lowercase, the first letter has to be in type, and thanks to parsers being sloppy with the specs, the chunk order doesn't matter much. So we can add extra data in a custom chunk even before, just after the signature, before the image header. So just after the signature, which is 8 bytes, and we control the first block of 16 bytes because we control the IV. So the idea would be to add a custom chunk to cover the data that's from the Google logo that will be encrypted. It will be ignored because it will be contained in the custom chunk. And the encrypted file will be valid because the Google became encrypted but hidden by this custom chunk, and the rest was pre-decrypted, so it's valid. So now, after encryption, we control the first block, signature of 8 bytes, and 8 extra bytes, which is enough to declare a chunk, luckily, exactly, no need of brute forcing. And this contains the chunk of the target, and then after that, the chunks of the target that were decrypted in advance and appended to the source file. So Janssen baptized this encryption. We are looking for a smart name, and he said, fuck it, let's call it encryption. So with 2 files. So basically, you have 2 original files, and you can create one single file, R, and that will show S initially, and after AES-CBC encryption, will show the next file. Okay? So here's the layout of the file before encryption and after encryption. The original file standard with what will be the target but pre-decrypted in advance. And once encrypted, we will manipulate the IV so that this declares a dummy chunk that will cover this, which we don't control, but will say, this is, just ignore this, and this is actually the chunk of the target. So let's do step by step. Just for the recall, the first time I presented this in the middle of a presentation in 6 slides, the whole presentation. Apparently it was a bit hard, so that's why I was asked to come up with the full-length one. Yeah, they suffered, I think. Yeah. Explain all this in 6 slides was apparently a bit tough. So, and they asked for a step-by-step walkthrough. So now, let's start again. We have the key, the source and the target files, encryption key, and this is our 2 original files from the web. So initial checks. The source file is a PNG. The PNG format tolerates appended data. The target file format, as you saw in the introduction, it doesn't really matter. The 2 source and target formats are kind of independent as long as they follow these rules. The target format allows custom chunks at the beginning of the file, right after the signature, which means inside the first block. The source file fits in a single chunk, because it's not the case sometimes. Sometimes the custom chunk cannot be too big. And the algorithm we will use has a 16-byte block size, which is big enough to declare a chunk after the signature. So 16 bytes is enough to put the signature of a PNG, declare a fake chunk without any brute forcing. Because if suddenly, remember, we were 16 blocks and the signature is 8 bytes, and the declaration of a chunk is 8 bytes. If I had 1 byte less, then I would need some brute forcing. So this is instant. Now we have the initial, we know that it will work, so let's go step by step. The first cipher block, so R starts with the first cipher, we'll start with the first plain text block from S, and once encrypted, R will become, because the target is a ping, so 8-byte ping signature, and a custom chunk that will cover all the chunks from S. S is this, which, if you remove the signature, is this size in chunks. This is encoded 36C0. And the custom type we'll use, it just needs to be lowercase in the first letter, RMLL, because that was the name of the initial conference I mentioned that. So basically, once encrypted, we want our file to start with this exact block. So now it was starting with this from the Google logo, and we want to start with this to cover the encrypted, the Google logo data once encrypted. So we have the P and C blocks and the key, which we set in advance. Now we just decrypt that and we XOR with P1. So we will get an IV. Remember this schema. So we will get an IV that will turn P1 into C1. And now the IV is determined. So now the encryption of the actual parameter is finished. We have the key and we have the IV. So we cannot change the encryption anymore. We just need to craft the file. So we just pad the source file. We encrypt this with our parameters. And at the end, so with this initialization vector, S will start with a signature and the RML chunk covering the rest. Now we add the custom chunk. So the chunk ends with the CRC32. We just need to calculate it with the encryption data. And then we append the original chunks of the target file. And we decrypt the result after padding. So now we have the file that will work in both cases, blindly. So this is how it works. We have this file made of the original signature, the logo chunks, the Google chunks, and some padding, and the pre-decrypted result, the pre-decrypted chunks of the DuckDuckGo picture. And then, after encryption, this will turn into what we wanted, the signature and the custom chunk, which will make all this hidden, the CRC that we calculated from this content, and then the rest of the DuckDuckGo picture original. So this here and this here totally transparently comes from the original and the source and the target picture. And the rest is just IV manipulation and creating a fake chunk for that. So this works with any algorithm, any source format, any target format. The source format should tolerate append data. Target format can fit a signature and a chunk declaration into a single cipher block. and the source file has to fit into a single chunk of the target format. And as you saw, with 3 days, you can even combine that two algorithms in the same file. And actually, the proof of concept I have ready for CCC is much more crazy, but yeah. It doesn't fit in a tweet. We can use algorithm both ways and with other file formats. As a demonstration, the first time I mentioned that was the magazine Proof of Concept GTF4 or Get the Fuck Out version 3. It was a PDF. And if you encrypt this PDF, it becomes a PNG explaining encryption. And even better, the PDF itself knew the IV, was telling you in advance the IV it should be encrypted with. Even this IV was depending with the, how do you say, the content of the PDF. And this was added as LaTeX level. So basically, by changing this value, you would change the content of the file, which was changing the IV. So it had to stabilize in some way. And luckily, it stabilized faster on Travis Goodspeed machine. So that, you know, it's like I can tell my key from my own content weight. By saying the different key, I change my content. Yeah, that was challenging. That was fun. And if you want more details about the other file formats, because here I only covered PNG, but if you want more advanced version, alternate version, then I did another talk, a bit more technical, I think, at Raumzeitlabor in May. And also, what I mentioned earlier, we actually, Axel April, decided to port that into Android. Because, as I mentioned in my previous talk, the Android zip parsing is not so good, and we decided to abuse that in a new way, so combining those tricks with encryption. So we present this in Black Hat Europe this fall about the Android version of that. Now, yeah, would be too easy. Yeah. So let's play with TrueCrypt, because why not? And also, yeah, it may be good. In my previous talk, I mentioned how you could hide data in a PDF. Now I'll mention another way of hiding data in a PDF. TrueCrypt creates, oh yeah, just for the funny story, I crafted this, the content of this, and 2 days after, independently at home, and 2 days after, the guy quit. But don't ask me, I have no idea, and yeah, I mean, but you know, my script was working, it's like, cool, and then TrueCrypt becomes decrypted, so. Travis Goodspeed said it's a good homage to TrueCrypt anyway, so let's wait. So TrueCrypt, if you don't know, creates a managed virtual storage volume, and it's encrypted, and it's transparent for the system. And the volume is useless without the password. So if we look at standard format headers, PNG, zip, JPEG, we see a lot of strings, even the name of the type and so on, a lot of understandable stuff. And if you take TrueCrypt volumes, the headers look like this, random. Why? So the TrueCrypt file format was designed not to be identified except if you have the password. So it has a random appearance. You can deny it's a TrueCrypt volume. There is a header, but it's encrypted. So actually, if you take this one, if you would decrypt it, usually it's never decrypted as file, but if you would decrypt it with the password, so then you see that it has a valid structure. But you cannot tell it's a valid TrueCrypt unless you have the right password. But the question is how many files we have that start with 100% random files. This is not so stealthy. And because of this, because of a file starting with pure randomness, this is actually an automated way to look for potential volume, TrueCrypt volume. Yeah, so potential volume detectors that could, like your laptop is taken, people parse all the files, and suddenly they see that it has no known header. It's probably big, the size is rounded to 512, and the content looks random from the very beginning. How many files do you have in a normal system that can be like this? Yeah, that's the problem. So, just before we go on, if the encryption only depends on the password, then TrueCrypt would be vulnerable to rainbow table attacks. And because of that, they added some salt. So the file starts with the 64 bytes of salt that should be random. And that combined with the password will be used to decrypt the header. which means you cannot pre-compute an attack on a TrueCrypt, because then you will need to get the salt of this exact file to brute force the password. Okay, and makes, well, okay, there's another reason, but this also helps to make rainbow tables useless. So this is the actual structure of a TrueCrypt volume, even if it looks random. This is the salt that with the password will be used to decrypt the header. And the header contains some parameters and also the key that will be used to decrypt the whole volume. So there are kind of two levels. Decrypting the header gives you the keys, and the keys gives you the whole stuff, right? And to get this decrypted, you need the salt before, right? That's two levels. So if we modify the salt in any way, we just need to decrypt the header and to redecrypt it with the new salt easily. That's the reason why, if you had a TrueCrypt volume, you could change the password without reprocessing the whole archive, because the password was only used to decrypt the header with the salt. So you could change this, and this is also why you had the option to kill, you had the option to save the header somewhere separately. So if you had a TrueCrypt archive, you kill 1 byte here in the salt or in the header, and the rest cannot be decrypted. This would make the keys not recoverable, so you couldn't decrypt this. And just by putting back the original header, you would restore the decryption. So if we modify the salt, we just have to recrypt the header. No need to change the volume itself, because the keys present in the decrypted header, the volume keys, haven't changed. So the idea was to integrate the TrueCrypt volume into another file. Stealthier, both formats still valid, so you can still use, so it's not full of randomness from the very beginning. Remember, you can bring back randomness afterward. Of course, it's not so stealthy if the file is fucking huge, but if you wanted some temporarily more stealthy TrueCrypt volume, it works. And it will also defeat automated detection. So the strategy, a bit like what we did with the cow and its micro SD in the stomach, was to modify the host format to create some space near the beginning, so create a custom chunk, similar technique, and then you copy the header and the volume's content. The decrypted header hasn't changed, the volume hasn't either. You decrypt the header with the initial salt, and you recrypt it with the new salt which comes from the header. And now you adjust the CRC if you need to. So let's see that in detail. So you have this TrueCrypt volume, and you have an image here. So first we create a fake chunk which has the size of everything with the lowercase name, so that, as you know, it will be ignored by the parser. Now you copy actually this whole part here. Here it's 64 bytes. So you can just put some spaces here, it doesn't matter. Now, we decrypt this content with the original salt, and we recrypt it with this new salt. The volume key hasn't changed, so the rest of the volume doesn't need to be changed. And this is just updated salt, updated header encryption with the new salt, which is actually a valid binary format header. So now, salt, it's French typo. So as a TrueCrypt salt, the header encrypted with this salt, and the volume content, the volume keys haven't changed. This is a valid TrueCrypt. As a ping, this was a valid header. This starts a fake chunk, and this is all ignored until the end of the chunk, and the original chunks are appended after. This is a valid ping. So this works. And POC GTF04 was a valid TrueCrypt, as well as the PDF being distributed. And that's one of the rare cases where it was a fully standard PDF file. And you can also do that with other formats. So the same technique that we use with encryption to make ignored the encrypted data can be used to hide a TrueCrypt volume. So, conclusion, for both cases, we can add extra data in a standard binary file. And in one case, this data can be another standard file after encryption or decryption, or if you want, a TrueCrypt volume. And as you can see, I still don't understand, I don't know how AES works inside. I just know encryption, decryption, key. Okay, good enough. I won't go further. But yeah, it's better to progress step by step with crypto or ask an expert, because it's you cannot, once it's, oh my God, I encrypted, but it's random again instead of a valid ping. What did I do wrong? Yeah, difficult to debug, I can tell you. But once again, encrypted doesn't mean it's random. And the proof of concepts are available here. Yeah, I didn't upload the RMLL one, the MRMCD. Thanks to these guys. Viork, Jean-Philippe Aumasson is a crypto architect. So that's the guy who helped me make possible, and all those guys helping me. And thanks for your attention. Random keys. Again, can I have a bigger font? No. No, I cannot have. So, and then you decrypt it. Yeah? Can you show some live demos with this proof of concept? Yes, but wait, I'm just, I just launched the script here to decrypt the MRMCD. And they were decrypted. So, where is it? Oops, 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 date. So, this is encrypted after AES. And this is, oops, yeah, decrypted after this. So if you look, you have a file that I made, and then you have the picture, and at the end of, yeah, it won't be visible. Yeah, it's difficult because of, it's probably not the easiest approach. Ping. So here, I don't have the zoom anymore. Why? Why I don't have the zoom anymore? Pourquoi tu marches plus, toi? Oh, it crashed. Oh, bastard. Oh, sorry. I turn on the zoom again. So here you have, no, it doesn't work. It doesn't want to work. Sorry, guys. I don't know why. Cannot zoom anymore. Can you see stuff? So here you have the PNG file and the custom chunk covering everything. And then at the end, you have, yeah, oh yeah, it really sucks as a view. Why the zooming doesn't work? Anyone knows? Yeah, but no, yeah, but usually the program was working. Can't you run? Piece of shit. It never failed me, this software. Ah. No, yeah, no, still no jump. Oh, fuck. Ah, okay, slightly better. So, yeah, we see the signature, then we see the fake chunk, and then if we look for IDAT, we have the end of the chunk, but yeah, it's not exactly visible. Yeah. Let's look at the other one for the PDF. So where is the font? Yeah. So here it's actually a handmade file of PDF, and then. So this is the image, blah, 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 blah. Hey, where are you? Yeah, then the trailer, and then it's appended data that will be decrypted as the file. That will be the content of both files. Yeah, maybe I have some easier proof of concept. On-site labor. Yeah, I went actually much more crazy. So proof of concept. Oh yeah, my proof of concept were funny. Yeah, her again. And it's unencrypted. You get this guy, random pictures again, as you can see. RSA security, that if you decrypt it, you get another random picture. Actually, yeah, I can't tell you who, but we were publishing this, and this guy's company was a partner of RSA, so we had some censorship here. So it was funny. That was the first time I had some censorship. And the JPEG, yeah, JPEG, because it's Adobe. And when it's decrypted, you get this. So once again, random pictures. So yeah, maybe I can actually go through. So that's my presentation from Outside Labor. No, maybe it will actually be more complex than show you the file. Sorry for that. Yeah. So in the case of JPEG, can I have better font? Yes. The FFFE is actually a comment chunk. So basically, you make this all being a comment. It's a different way of putting a micro SD into your JPEG cow. And but the thing here is that the size is only encoded in 2 bytes, so you are limited to the size of the file. And in the case of PDF, it was actually quite difficult because can I? Yeah. Oh yeah. Sorry for that. No. Yes. Because the PDF to declare an object around a custom object in PDF takes actually more than 30 bytes. With the usual syntax, like a percentage PDF dash 1.5, number of objects, dictionary, etc. So here, I was really lucky because I truncate the signature with a null character, then I do an object declaration without any number, then I put no compression, no dictionary parameters for the stream, poof, just 16 bytes. Whew, no brute forcing needed, and compatible. So that's the way you create a dummy object in PDF of any length. I mean, in a very optimized way for AES, because AES is 16 bytes. If you would use a better, not a better, but a block cipher with bigger blocks, then it would be easier. But I stick with the AES from the beginning, because that was my initial challenge. And then you create a custom chunk, and then that was the encrypted data that was Angela, right? Angela as a PDF. And once again, PDF completely tolerates that's the stream, and then it doesn't matter if after the end of the file, whatever you put here. So PDF is totally tolerant with appended data. Yeah. Any question? Yeah, it's it's tolerated by most software as far as I know, perhaps not the macOS and the Firefox one, but it's absolutely not standard. Even the signature is truncated. Like it should be %PDF dash 1 point something, and here at the %PDF dash null character. Stop here. So yeah, that worked. Sorry? Louder, please. Yeah, sorry. The question was that was the PDF, the truncated PDF signature standard or custom? So was this implementation of the signature according to the specs or not? And it's absolutely not according to the specs. But still, it works with most tools, whether they are official Adobe or standard ones. So that's why we decided to use it. Any other questions? Sorry for not repeating the question. Yeah? Oh yeah, a TrueCrypt hidden volume is just a volume at the end of a TrueCrypt. So that's the file is still 100% TrueCrypt valid. So you could still use a hidden volume inside it. And following my previous talk, you could also hide data in the PDF. Why not? With the schizophrenia. Oh. Yeah, sorry, I didn't repeat the question again. No more questions? Thanks for your attention.